So let's get started. So, hello everybody. So today we are going to be setting up page tables for executing our quote-unquote calculator process, which is, in case you missed it last time, is was it Oops, calculator source main is literally just move dead beef into racks and then syscall. That's all this does. And so what I have so far is I have loaded the elf. I've embedded the elf into the program using the embed file built-in function, and then I am parsing using Zig's elf parser library. And what I do is I go through, I basically collect all the pages into some information I can understand that has a destination address, which is the actually it's destination virtual address. It's the virtual address that the page will sit at. This is the actual data that will be copied into that page, and then it's and then whether that page is executable or writable. You cannot have something that's both writable and executable. So second. So what I've done so far is I loop through I always get confused. What Elf has something called segments, and Elf also has something called sections, and it's always kind of, I can't believe they use the same word, use synonyms to describe two different things, but whatever. Well, I can believe it because that happens all the time. So I loop through the program headers, and the program headers describe I'm actually really forgetting. I'm forgetting what it's called, a section or segment. Program header. It's actually going to bother me whether section. Yeah, I think they're sections. I don't think it's a segment. I think segment. Segments contain information at runtime. Sections. Oh, I'm wrong. It's segment. So the program. So I'm looping through the segments, which contain one or more pages, and then I just kind of loop through the address. I kind of just do one page at a time. And I'm sure there's more efficient ways of doing it, but this is the easiest way I can think of. And then what I do here, I loop through the alpha, the segments, loop through the pages, collect all the pages with this extra data, and then I create an arena allocator actually for the application. This arena will store all the page tables, the pages themselves, and possibly some other info for this application. And then and so I just use this arena to allocate the pages and the page tables. and then I will use this code kindly provided to me by somebody on OS Dev, on the OS Dev Discord, and use that to launch into userspace. So let's get started. I have begun already parsing the page mapping level 4 table and creating that. So what I do here, so for each page descriptor, so I call them page descriptors, it describes each page. We have the destination page, which is the actual page that will hold the data. And then we need to calculate the offset because the segment may start as an offset into the page. It may not start on a page boundary. And then we copy the data from the segment into the page, and then we start parsing the destination address, which is a virtual address, to construct our page tables. So yeah. So here we basically, the idea here is that we're going to construct one table. We're going to loop through the virtual address and then kind of lazily instantiate the page tables if they're needed. Basically, if the entry in the page table is 0, then we will allocate a new table for that, and if it is not 0, then we will follow that page table into to get to the next level. There is probably a more efficient way of doing this, but this is the most obvious and least error-prone way I can think of right now. And then one of the tricks I'm using is that I am actually storing the current address of the page table as the entry that the kernel can understand. And then once this is all done, then I will do a pass through each table to change those from virtual addresses to physical addresses, because you need the physical addresses in the page tables. So let's continue here. So right now I have the page mapping level 4, and so we're just gonna kind of like so this is the page directory. So we have the page mapping level 4 table. That's at the root. There's only one of them. Here now we construct the page directory pointer table, and then we're going to keep going down. So next is the page directory table, and this will follow a very similar principle. So we want to get the table, and so actually then now we need the page directory pointer index, which is gotten from the mask. So page directory pointer table. Here I'm abbreviating it for some reason, and then other places I'm not. Whatever. And so I just want to double check that this is the right formula. I already do this here when I map the virtual address. So we add an extra -9 here. So yeah, and then we shift the mask right, and then so we have the page directory table index, and then which means that we want the actually, can this be PML4T? Okay, no, it can't be const. So this is the page directory pointer table entry. And that is the page directory pointer table at the index of this. And we will do something very similar. If actually, I don't know if this is right. We want to hold on. Don't we have an assert somewhere? Yeah. Yeah, this is not 100% correct. We need to and off the the auxiliary bits here. I'd keep it there. There are some bits that are stored in the entry that is not the address, and so I'm masking those away, so it actually becomes a real address. Give me 1 second. Okay. All right. So uh, so the next thing is, yeah, so we need to mask this off, and we have this assert here to make sure that that when we end this off, this entry off, then basically what this is doing is making sure that, well, when I allocate the actual table, that it it's on a page boundary. That's really what it does. So okay, what else? Actually, this might not be the right mask. It might be a little bit. There might be a couple more bits sliced off. Let me check that actually. So if we look at, so what I've been Googling is page table cheat sheet. And there is a MD64 page table cheat sheet. And there's this image right here, which is taken directly from the manual, but it's nicely placed in a Stack Overflow that somebody kindly screenshotted for us. So here, the address of the page table. 1 second. Reserved, ignored, protect key. So this is how, yeah, this has the protection key. So ignored, reserved. How many bits is this? I think this is was it 40? Is it 48 bits? I mean, it's just is it 52 bits? I guess. Address of PML4 table. It's fine. And then what? bit is this? So bit 63, 62 to 60, and then reserved. What is M minus 1? Let's just look in the, let's, all right, manual. Let's look at the manual. Page table. Or like, let's look up like a bit or something, like the global bits or something. Is it not? There's like 4 different volumes for this, so it may not be in this volume. But pretty short, like page mapping. Yeah, there we go. Yeah, I think it's just very slow. Page mapping level 4. Can I like search in here? Page mapping level. And like the frustrating thing is that sometimes they put like dashes like in random parts that are inconsistent throughout the oh, I think I just saw it. Like you'll see like some name like page mapping level 4, and then like one place they'll put a dash between mapping and level, and then in another page they don't, so it makes searchability very hard. Global. It's a global bit. Global. Or supervisor is another word. This is it. Okay. No, I'm right. This will definitely have something here. So we want the 4 kilobyte one. I do want to support 2 megabyte paging. So yeah. So this goes up to 52 bits. Okay, cool. So let's do that. So let's actually mask off more than this. So what is 52 bits? Is that like this? So this is, what is this? This is 32, 48. Wait, sorry. 16, 32, 48, 52. And then this would be 56, right? 60, 64. Okay, yeah. So this is 52. So this is the mask that we want here. Actually, so this is, let's make this const of 50 virtual, like 52-bit mask. It's dumb, but whatever. I'm sure there's a better name for this. Is that better? No. Let's just keep, let's hard code it, because I feel that's better. Anyway, all right, so let's get back to this. If, so we will literally just copy this and then replace PML4T with this. Same thing. And then Can we scope this? We might actually need to be able to scope this. And then yeah, let's try scoping this as well. Okay, so this is PP entry, and then yeah, and then we allocate, and then we just do this. I don't know what would be faster, typing out the search and replace query or just double clicking and doing this. I have no idea. Whoops, wrong thing. Actually want this. Okay, and then this becomes that, and then we do this. Then so wait. All right, yeah, good. All right, so the page directory table. So let's stop here. Let's not get too ahead of ourselves. Let's make sure that we can actually, like, a search don't catch or something, and things compile. Okay, cert is not declared. That's fine. Cert is equal to utils.cert. I really should actually just. I think I'm gonna. Utils is gonna kind of be my like common library I'm gonna use here. So I think at some point we need to do some refactoring there. Visual mode. All right. Incompatible types. 549. Oh, yeah, we want to break. We kind of want to do one of these. And then this becomes, yeah, it's literally the same thing. Use of undeclared identifier page directory pointer table. Okay, that makes sense. Yeah, let's do this. And then this will be, we'll just This will be this type equals undefined, and then yeah, we'll do a similar thing here. Okay. Yeah, and same thing here. Okay, so that ran. Alright, so let's just run this in debug mode, see if we don't have some weird stuff going on. Alright, so it worked. Okay, cool. And in case you're interested, these are the two segments. One segment starts at hex 20,000, and it gives the I think this is which we'll call it. I'm trying to remember. I think this is like the read-only data, and then this is the actual code. And there's no, it doesn't reference any globals, so this won't even be touched by the program. This will be touched. So yeah, so nothing, no asserts fired, no panics. Seems like we're in good shape so far. All right. And maybe for like sanity, we should probably like print out like the tables and stuff like that, the table addresses. Like, actually, where is my, what prints do I have here? Yeah, let me get rid of this. So print, oops. Let me, yeah, my fans are really spinning up here. And then we will PML page mapping level 4. I will. I like have to say it out loud for me to like remember what the acronym is. And then this is the page directory. Oh, the page. We'll do the page directory pointer table, and then the page directory table. And then and then page directory pointer table. Alright, so let's see what this says. As far as I understand, each of the first indices should be filled so far, I think. Maybe not the page directory table. gonna barf. It is not working. That is not a good sign. Like maybe let's do something simple. Let's do like, instead of it like trying to print out the table, let's do like .1 or something. Okay, that's fine. Actually, let's do 0. Unrecoverable error. Cast causes pointer to be null. Well, okay. Where is that? That is not. That is not a good stack trace. Unless it's doing something weird. Yeah, no, that's not a good stack trace. Let's check graphics 119. I think it has something to do with hold on 1 second. It might be like a general protection fault being masked by other dumbness. Let me see. Graphics, typic graphics. 90, was it? Yeah, 91. Oh, kernel 138. That's it. That's right. Yeah, it's saying that this RSP is 0. 193. Yeah, it's a general protection fault. Yeah, let me comment this out. This like doesn't work. This crash dump to. I have to when it does like when I do this into pointer stuff, I have to if it's 0, then I have to conditionally do something else. Yeah, general protection fault. That's okay. You know what? Let's fix this. This is kind of a deterrent, but let's fix this. Bytes to value. Turn better. Maybe I'll do something like this. Like if regs.rsp is not equal to 0, then do this. Like else 0 or null or something like that. Because then we don't want to print this. Or actually, no, it would just print it. And similar here, like if regs.rsp is not equal to 0, then do that, else null. Or is there a better way of doing this? Hold on. Instead of sticking all this stuff in here. So ss. Yeah, the register dump is fine. So the return address returns, like, yeah, all this stuff, like if regs.rsp, hold on, we'll put this all here, and then like if regs.rsp is not equal to 0, then we'll do all this stuff. Then that should work, actually. Uh, 138 again. Or 196, 138. Oh, okay, similar thing. Like, and then we'll do if regs.rsp is not equal to 0, then we do all this fun stuff. RSP, let's just make sure. Yeah, and then this is all based on return this, return that. And then we want to add the error code. Now, yeah, the problem here is that whatchamacallit, is that the return code is on the stack. So if the stack is 0, then I don't know what to tell you. Oh, this goes here. Okay, integer overflow. Okay, kernel 199. Joe protection fault. So it actually did do something. And then it kind of barfed when trying to print this out, I guess. And then we have integer overflow. From GUI 216. So it's saying 216. So I suppose it's this C right here. So there's a glyph? That's... Am I putting some... Alright, let's do this. If C is... I'm really curious, like, if C is less than... Like, I don't want to check this for everything, but I do want to see what character it's printing out. That's, like, really weird. Oh, it could be 0. So if it's 0... so I wonder why... I'm going to assume if C, is less than space, or C is greater than what is it? Is it tilde, or is it... Might be tilde. Oops. Yeah, you see, like, I even have this in here. I do actually have this check everywhere. I guess I'll... yeah, I guess we can do that. Though I should probably, like, print some stuff out here. That this would be, like, to do, like debug if this, like, or put else, like put debugging, put here, something like that. Still an integer overflow. So we don't have this 216. Wait, if sorry. Oh, I'm doing the opposite. What we want to do is this. If this greater than or equal to, and then less than or equal to that. And now I'm let me make it consistent, because that becomes inconsistent with the rest of the code. What we want to do is put this here, do that, put that here, and then this is continue. Okay. All right, general protection fault. Okay, so we do have some stuff. Unfortunately, it goes off the screen, but at least it's something, I guess. So let's see. So it says XMM5 is a. So this looks like an undefined or something like that. So this is coming from kernel 199. So yeah, though this doesn't tell us anything, because RSP is 0 somehow. So I have no idea how RSP is 0. Do I support like new lines anywhere? I don't think so. Yeah, that's the problem, is I don't really support new lines. I suppose that's fine, because we have this. At some point, we're going to need to fix this. Support Turing complete markup in labels. Support Turing complete markup in labels. Yeah, let's not do that. Turing, debugging, graphics. I think I fixed. There's like some stuff here that I didn't fix. So, debug strings. Some strings are printing. Some strings have a null character in them when a GP fault hits. Debug in the text width function. The other one is support new lines in labels, or like some like markup tech. I feel that's a problem waiting to happen. Yeah, just new lines. Let's not go crazy here. Alright, so somehow we have an RSP of 0. Don't know how that happened. Let's look that up actually. General detection fault RSP 0. Because I'm not doing anything weird like an IRET or something like that. I mean, like, I'm sure it's, like, I mean, I'm just going to waste more time on this. I'm sure it's coming from one of these things. Like, if I just do PML4T, that should work. So let's do some process of elimination here. And then let's just do, like, this, and then only this, because this should allocate cleanly, because this is just allocated, like I don't do any weirdness here. Too few arguments. Okay. Actually, let me see what was like the I'm curious. Oh, I don't dump the segment registers. Oh, error code is 0. Return address is also 0. So that the return address is 0, so that doesn't help us. Okay, so that worked. So okay, so that's reasonable. And then, okay, so let's now add in PDB. Let's add this one in. So that worked. Does this work? So this, all right, so this is undefined. This is what's causing a problem. All right, so, okay. All right, so that's something. So the page directory pointer table. Oh, because we have to memset all this stuff. That's why. That's what's killing everything. This is why, if you see up here, I want to use a custom arena allocator. I hate that Zig automatically puts. I mean, I understand why it does it, but and I don't think there's like an alloc advanced cleared to 0 function here. Like, is there a 0 function or z or something? There's a dupe z. No. So I have to manually memset this. So that is why this is happening. So we'll do this. So this becomes table.len. Index out of bounds. Uh, 590. Oh, this should be index. That's why. Okay, so we have some reasonable address here. Cool. And now we should have, and now we need to put a memset here. Okay, PDT is 0. That is okay. Because it probably will be 0. Alright, so let's see how this handles this. Okay, cool. So, so this worked. So we have, yeah, reasonable, and then the page directory table is, must be later here. Yeah, there has to be something here that, right. Oh, no, it won't have anything. That's fine. Because we haven't populated the page directory table yet. So now the page directory table will have a similar thing. We will have a page table. It'll be very similar to this. And then, yeah. And then we will just copy this. We can probably, honestly, we can probably make a function out of this. like construct. I mean, the only thing is this mask here that changes. And then we like we'll change this from PDPT to PDT. Then yeah, same stuff, and then this becomes the page directory table. Pointer, okay, and then that's okay, and then we will do this again, and then we should have an entry in the page directory table. Guess we don't. Oh. Oops. This is page table. Okay, yeah. Okay, yeah. So this, all right. So this has a nice entry. Yeah, it's the second one because the page is like starts at like 20 quadruple 0 or something like that. So all right. So we have that. So next is the page table, and so now we have the page table entry. So we can do this, and then what this will do is yeah, and then there's this page PMLE page size control, but actually that wouldn't go here, that would go here. And this is like, we would set this to 1 if we want 2 megabyte pages. So the page table entry is the physical address. So we'll already have the physical address here. We don't need to do that in like the past or something like that. Okay, so it's present, it's writable. Yeah. So all this stuff. Page directory table, and then we'll do a page table. Oh, and then the page table entry, obviously, the page. Then we need the page table index. We don't really care about the mask anymore, but whatever. So page table index is equal to page table entry. So let's see how this works. So if there are no issues here, I think I'm gonna cut it off here. We've been running an hour. Or so this is the page directory table. That's fine. Okay, so we had no issues here. Out of curiosity, what is this formula? Actually, instead of cutting it off, I may pause it for a little bit. So that's 12. Okay, that's 12 bits. That makes sense, I think. Yeah, because that's a page. All right, give me 10 minutes. I should be back in 10. Be back in 10 minutes. Whoops. I don't want to save that. All right, be back. Okay, I'm back. All right, so where were we? All right, so we had the page table. We constructed the page table. Uh, and yeah, exactly. Yeah, they shift the mask down, and so yeah, so this is the page table, and now we want to print the page table. Page table. Um, okay, here's the page table. Yeah, and this looks right. The first page is no execute, but the second page is execute. So you have this 800 stuff, and then this is this is an executable page table. Yeah, this is not writable either. Okay, yeah, none of these are writable. So okay, so we have the page tables. And so the next thing we need to do is actually starting from the page mapping level table. Here we need to start up all the way down to the page page directory table. We need to replace all of the pointers there to the physical addresses. So basically we do where is that page mapping level table level 4 table, and then we go through each entry. PML4 table entry, and then if is equal to 0, then we continue. And then we just kind of recursively go through this. And so we want to get the and this is why, actually make sure that we're outside the loop. Okay, we're outside the loop here, so none of this, like the page table, this is out of scope. So we can actually assign stuff here. So we can take this. So page directory pointer table, is equal to this entry and this mask. Yeah, we can literally do this. And so that's the page directory pointer table. And now what we need to do is then replace the entry in here with the physical address. So it's a little bit tricky. We can't just assign it. So what we need to do is kind of OR the bits in. You know what? I just realized something before we do any of this. Oh, actually, I don't need to do that. Whatever. Let it run. So, actually, one of the things I'm realizing here is that, you see the page mapping level 4 table here. This entry is no execute. But that doesn't work for this page table. Do I not set this bit here? Let's take a look at the manual then. So, no execute. Alright. No NX bit provides the ability to mark a page as non-executable. If the NX bit is set at any level of the page table hierarchy in the table, the page mapped by those entries is a no execute page. Okay. Alright, so what that means is that we cannot apply the no execute bit or even the writable bit, like, until we hit the page, until we hit here. Right, so like this is writable, and then no execute, like no execute has to be 0, and then is writable always has to be true until we hit the page, I guess, right? Because yeah, I think that's how it has to be. So if we get rid of this, and then is writable is always true, right? Then we do the same thing here. No execute is writable is true, and then we just no execute, then is writable is true, and then only when we get to here we start doing we add these permission bits in. So now this will look slightly different. Which actually makes things slightly easier. with this stuff, because now we can assume that everything left of the first 12 bits, we can mask off the first 12 bits, and then just paste it into the new entry. Like, we don't have to take things out of the middle. We can just take things off the left, which makes things a little bit easier. Let's see. Give me 1 minute. Okay. Yeah, I'm back. Okay. All right. So let's see what this prints out. All right. So, yeah, the no execute bit, we're just setting the right bit. Page table. Is writable should be set. Oh, I'm sorry. Wait. No, that's fine. Yeah. So we have 7s all the way down until we hit here, and then we have okay, great. So yeah, no. So it's executable, 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 writable, executable, writable, executable, writable. Not executable, not writable, and then executable and not writable. So so yeah, cool. Let me read this a little bit more. The execute protection is enabled by setting the NXE bit in the effer. Oh, we have to make sure that that's set then. We can actually print this out of this loop. Print it over here, and then let's print the effer register. I always forget what effer means. I think it's like AMD 64.get effer or something. Yeah. Oh yeah, because we want to put that in here. Oops. So is the no execute bit set? All right, effer, system call extensions, sure, long mode, no execute enable is true. Okay, good. All right. All right. So we have that. Now, what I'm hoping, I'm hoping that it's okay that I'm setting writable and executable at the upper levels. I feel I read somewhere that it has to be like an exclusive OR with like the right bit or something. Read write bit in the page. If read write 0, the page is read only. If 1 in all of the page tables traverse, it's read write. A page fault exception occurs if an attempt is made by the user to write to a read only page. If that's actually pretty cool. Then you can do so it's a page fault, so you can handle it. Yeah, what that means is that if you write to it when the write bit is set, then the kernel actually has a chance to reverse that decision. I don't know if I use that because there's also the present bit, which is what you would use. What is it called? Yeah, there's an is present bit which does a page fault, which is typically what you use. If supervisor software attempts to write a read-only page, the outcome depends on the value of CR0 write protect. Probably want to set that bit up on. We probably don't want to write to a read-only page table, even in the kernel, for security reasons. So okay, all right. So we got something. Yeah. So page directory table. So that means that we have to replace this with the physical address of the physical address of the PMLT entry table, actually. So actually what we want to do, we can do this. Const PML for table address is equal to this. And then this becomes that. And then do that, and then we OR in the entry, and then we only take the these bits and OX FFF. So that actually should work. Let's see if we get any compile errors, actually. Far. Or does const work? I wonder if const works. Yeah, it does. So we have that. And then next is the page directory table. All right. So now we have the page directory table, which is, so we'll do one of these. The page directory pointer table address is this, sorry. Oh, yeah. So then we loop through this, actually. And yeah, so this is kind of a nasty algorithm. It's n of 3. I'm sorry, O of n cubed algorithm. So it's, but the thing is, it should be relatively fast because most of these entries are 0, and there's only 512 entries. So that's kind of its saving grace. So table, and then we will have PDP page directory pointer table entry, and then J, and then or what we can actually do is this will be the index instead of doing I, J, and then similar here. This will be the index, and then similar here. If the entry is 0, then we continue. The only problem here is that we want to make sure, we want to think about if there's a case where we're going to do this twice. Like the entry here, like we hit the same page directory pointer table and then we replace all the physical addresses. Yeah, we replace the physical addresses that are already set. So we probably don't want to do that. Okay, we might need something better here. Because what can happen, I think in this particular case, this will not happen. But in general, what can happen is that we can like loop through, we can be using like the same table in different entries. And though actually, maybe the way I've done this, because this is not the most efficient way of setting up the page table, is I don't think I reuse tables. Like I create a new table. Actually, this will work because I will not do this more than once because I create a new table each time. So that is okay. This is not the most efficient way to set up the page tables, but it is the easiest to think about or reason about. So, of course, a future date we'll need to rewrite this. Or at least it's the easiest for me to think about. I don't know about other people. Okay. So we'll do the same thing here. The same exact code except one level down. So this becomes, instead of, so we'll just do this. PML4T will become PDPT. Yeah. Yeah, and then this will become the page directory pointer table. Or, wait, actually no, I don't need this. I can pass this by pointer and then save it. Actually saves me a little bit. I could do this. And then this will become, so this is actually easier because then this becomes that dot star. And then we do that. Dot star. Yeah, and then we do the same thing here. Dot star. Dot star. And this becomes the PDPT. Dot star. And then the page directory table. And the page table we don't need to do because that already has the physical address. And then, oops, no, this goes in here. So this is the page directory table. And page directory table. And then we don't need to touch the page table. And then that's it. That we can move this print down here. Uh, 60. Where is this? 643. Oh, yeah. Yeah, we don't have the page table. Let me just make sure PDPT. Just make sure that that I didn't miss anything here. All right, so this works. Now let's run it. Okay, so we've got something here. 1D2, 1D2. Yep, this looks like, so if you see here, this is the virtual address, and then this is the physical address. Okay, so we actually have set up the page tables. Or at least it looks like we have set up the page tables. So really, the next step is to start up the is to actually execute our application. So I think I'm actually going to cut it off here. Because I don't have much time left, and this will probably take me a lot longer than I expect it to take. So, so I think I'm going to leave it here. I will upload this. I will upload this stream to YouTube since it's relatively successful. I haven't been uploading to YouTube to the streams that I don't really. I kind of fail in the end, but this one is actually a successful stream. So I will upload it to YouTube. So yeah, so I will probably stream maybe this weekend. I will see. If not, then definitely next week. So yeah, so thanks guys for coming out, and I will see you next time.